So welcome back, everybody. Or, yeah, everybody, in one form or another. I heard on the news yet other universities switching to online classes completely. I have to say that if the format that we have here, if that's what we have to do, I think it's going to work for us, right? I'd like to think that I was being exceptionally planful by doing things the way that I do, but I think I'm just going to luck out. So we will be Zooming if it comes to that. You'll still be able to access the online homework system, and we'll do office hours via Zoom, which I already do. I keep the Zoom window open during that time as well, so we will make it work if that's what it comes to. So in terms of logistics, I put up this morning your third homework. Ding, that's not a doorbell. Okay, that's someone else's noises. It is going to be due the Friday after spring break. So you have 2.5 weeks, or at least a full week and a half if you discount spring break, which you're perfectly allowed to do. You know how to do 2/3 of it right now, and hopefully by the end of today you'll know all of it. Thursday at the absolute latest. That way you'll be able to work on that. And I'm not going anywhere for spring break, so if you do want to try and work on it, I'll be happy to answer questions via email. The other thing that we have is formative assessment number 3 due tomorrow. So if you haven't done that already, please work on that. That way we can go over that on Thursday. Also on Thursday, I am hoping that we can go over homework 2 as a group. In particular, the drop-down questions that seem to give some folks some issues. I'd like to explain that a little bit more, but I can't do that until everyone turned it in. So if you haven't turned it in yet, if you could do that, try to do that by Thursday class, that would be great. Okay, Willie, gotta mute you. Will, can I mute your Lecture 4, I find it highly unlikely that we can start that on Thursday. If we do end up running out of stuff to do and it's going to happen, then I'll let you know. Otherwise, we'll post that the week after spring. Any questions on dates, logistics, any of that kind of stuff? All right. Then we can keep talking about models and modeling. So
hi, good. How are you?
I'll let you look at the nice beach view while we think about this. What do you remember from last week?
Yeah.
Linear models, yeah.
Okay.
Tell me about linear models. They're linear, but is that a restrictive thing or is that okay?
Got it.
Yeah, so the term linear model, that term does not mean that we are restricted to only looking at linear relationships. That's the linear model means, let me pull up.
Exactly. Yeah, we don't want that again.
Linear model means this format.
Okay, well that'll make sense to me. Thank you so much. I will turn my.
Hey Lisa,
can we have the
Zoomers mute? We can't hear you.
All right, it looks like, there we go. It looks like everybody's muted now. So is that better? Yes, okay, good. All right, thanks guys. Oh, I'll just keep the chat window open. Thank you. Okay, we'll put that over here. So yes, linear model is this form, constant times variable. But that doesn't mean that it's only linear relationships. We've started with linear, but we're going to move on from that. So when you said linear model, is this what you meant, or did you mean linear relationship, Jacob?
I think that's what I meant.
You think you meant it?
I think that's the one that I meant.
Okay.
Like yeah, because it was like a beta 0, a y1.
A beta 0, a y1. Let me get up a picture. How about this picture, slide 15 in lecture 3. Here's some betas. Yeah. How about we look at this picture and do a little reviewing. So empty model, what does that mean? And the empty model is right here for context. What does that word mean in this context? No. Say it louder. Don't mumble, because I think you're right. No what?
No values placed in it yet.
No values placed in it yet. No predictor variables placed in it, yes. The term empty means that all you have is an intercept. Everybody has the same predicted outcome given by beta 0 right here. That's our intercept. Everybody shares it. So in this slide, we're predicting family income in thousands as my y sub I. That's my original outcome in the data set. Beta 0, that's my fixed intercept. It works out to be 40 in these data. So everybody's best guess for income is 40. E sub I, what's that thing in blue? What was it? It's individual specific, but what does that convey the idea of?
Estimated value.
The opposite.
The error.
Error, the error from the estimated value. So yeah, E you can think of as error. You can think of it as residual. Residual is the term that I tend to use most. It's how far off your predicted outcome is from the real one. So for this particular individual up here who went to 20th grade and makes $155,000 a year, his E happens to be, or her E I should say, happens to be 115. But we don't care about what E is for each person. What E really represents in this model is the idea that we expect that our model is imperfect. We expect there's going to be some differences between what we predict for somebody and what they actually have as an outcome. What we care about, how we quantify how good our model is at predicting, lies in the variance of the E's across persons. And so in this case, that's given to you as this formula right here. It's y sub I minus y hat. So that's how far off each person's actual outcome is from the y hat that's predicted for them. So E goes into this parenthesis right here. Let me get a better pointer option here. Apologies if anyone has a cat that's watching with them. It happens, right? I've heard from people that their cats attack the TV or the computer screen when they watch my lectures and I do this, so I apologize in advance. So across people, the squared differences summed across people divided by n minus 1 of these residuals is 1980. Given that this is an empty model, given that all we're predicting for each person is the same fixed intercept, this 1980 is all the variance in income that there is. This is the jumping off point. Everything is unknown at this point. So relative to that, now we can do better. Now we build a model, a linear model, to make a custom prediction for each person based on their predictor information. So first predictor we're adding in here, in this unit we're just doing one at a time, we'll get to 2 or more next time, is each person's education, so education sub I, that is a variable in the data set. And what does this minus 12 part here mean? How many years they went to school is the scale of this thing is years of education, but what does the minus 12 here represent? It means high school, but more specifically, what am I telling people by saying that what is going in the model is education minus 12? How many years beyond high school? So there's a word that goes with this idea of subtracting a constant. Centering.
Standard. Oh,
So yeah, education has been centered at 12 years. Centered such that 0 in the predictor variable that goes into my model means 12. The reason that I do that is so that this beta 0 right here, my fixed intercept, is something useful. The intercept is the you are here sign of the map of your data. You got to know where you are before you know where you want to go. The intercept, by definition, is always the same thing. It is the expected outcome when all of your predictors are 0. That is always what an intercept means. In this context, it's the expected family income. When my predictor X here is 0, that happens when somebody has 12 years of education. So putting that together, beta 0, my intercept, is the expected family income for someone with a high school degree. That's my reference point. Relative to that as a reference point, the model's slope for education, which is this beta 1 here, tells me what is predicted to happen to income for each additional year of education. Each additional unit of X more generically, but in this context, X is years of education, so beta 1 is the expected change in income per additional year of education. The math works out to be $27,000 of expected income for someone with a high school degree. For every additional year of education, income is expected to go up by 6.6. For this particular individual who went to 20th grade, 8 years past 12th grade, their predicted income is now 80. So you see the Y hat here? Y hat is what is predicted by the model. After you count for what's predicted by the model, the 80E is what's left. So for this person, now that we've factored in their education level, the difference between their real income of 155 and the income predicted by their education level, which is 80, is 75. Their residual is 75. It used to be 115, so that's better. If this model was perfect for this person, what would their residual E be? What's the best E can be? 0. E is how far off. E is a discrepancy between what is predicted and what actually happened. So the best E you can have is 0. So if we calculate the variance of our new E's, the E's that are left after factoring in education, the formula is the same. So where my cursor is here at the bottom, Y sub I for each person minus the Y that is predicted for them, Y hat. The difference is what predicted for them means. It now includes education. Square that, sum it up, divide by n minus 2. And it's 2 now because we had to spend one more point. We have to know beta 0 and beta 1 to be able to make this work, and that's what the n minus 2 reflects. Now the variance of the E's is down to 1594. So less variance is good. That means at least part of the reasons why people vary in income has been explained, has been attributed to education. All right, how are we doing? Now, how do we know if 1594 is really different than 1980? How do I know if education helped us?
Hello?
I can eyeball it. 1594 looks different than 1980. But wouldn't you like a more generalizable, empirical way of making that? Not just, it looks good to me. Yeah.
So
What we need is to understand whether or not this slope of 6.6 is different than 0.
So we need a Pearson.
Note the words different than.
Different than.
That implies the use of a two-tailed test, a two-sided alpha, meaning that I'm willing to say it's significantly greater than 0 or it's significantly less than 0 ahead of time. I'm staking my claim on one side versus the other. So to find that out, we need to know some additional stuff about the slope of 6.6 besides just what it is, what its estimate is. There we go. We need to know at a minimum its standard error. Once we know those two things, we know everything else. Everything else is some combination of those two pieces of information. So the estimate, that is our best guess as to what the slope is for our predictor given our data. The estimate is the one that makes those sum of squared residuals the smallest. That makes the set of e's the smallest they can possibly be. Mathematically, that's what defines what the slope should be. It's what's known as ordinary least squares estimation. We also have to know how precise the slope is. We need to know if we were to repeat this over and over and over again, how often will we get 6.6 as opposed to 6.5 or 6.7 or 9 or 0? We need the standard error. That's an index of imprecision. If standard error is higher, our slope is noisier. We would expect more variation in what that slope is across repeated samples. And just like we had the standard error of the mean, that told you how far off the sample mean is from the population mean, the standard error of the slope, homework question, tells you how far off that sample slope is from the population slope. It's the exact same idea. If we take our estimate, divide by the standard error, that gives us our t-value. That's our t-test statistic. That helps us locate where our slope is in the realm of expected versus unexpected. Question? The population slope, our best guess as to what it is the one that we got from our data.
From our sample
The empty
data.
model doesn't have any slopes in it. So let me go back, empty model is right here. Empty model means no predictors, no slopes. This is only an intercept. So down here, beta 1 is the only slope that we have so far.
So it's got 2 degrees of freedom.
We don't have any choice but to say this sample slope is our best guess as to what the population slope is. But the standard error that's around our slope helps us get an indication as to how variable that slope estimate would be if we did have more than one sample to draw from. So in this example, we have, let me go back. Here's some numbers to go with it. This is slide 17. The standard error for any slope, if it's a single predictor model like we have here, only one predictor variable and one slope, it's a function of the residual variance of the outcome, y, so how much variability is left over, sample size on the bottom, so more people means more precision, means smaller standard error. K is the number of fixed effects, so the number of betas we had to estimate to pull this off. And then last on the denominator here is variance of x. That helps to adjust for the scale because it's units of y per units of x. We got to have units of x in here. Units of y is already in the numerator. So all things being equal, your slope standard error will be smaller. The slope will be more precise when you have less variance left over and when you have more people. Once you know your slope estimate and the slope standard error, then you can make a decision as to whether or not that slope is expected versus unexpected. So the slope standard error works out to be 1.35 in this example. I can plug that into my t-test statistic formula, which is the slope estimate minus, I have 0 here as a placeholder for the null hypothesis. In this case, we're just testing against a slope of 0. You can test against whatever null hypothesis you want, but that's the one that's by far most common. And then divided by standard error. So it looks like we have our t-value, which wrapped itself around here, is 4.9. And let me go to the picture. Here's our t-distribution from lecture 2, slide 17. So we're at 4.9. Where are we in the distribution if t is 4.9? Way to the right. Let me get my my pointer thingy here again. There we go. Yeah, we're way over here. So we have to know whether or not that's expected versus unexpected. And we have decided ahead of time where that line should be.
It's our alpha.
That's another way of saying that is that we have selected an alpha. Alpha is the probability of observing an effect that big if the true effect, the null hypothesis, were true, which in this case is they have a slope of 0. So this t-table here tells you what the cutoff should be for when t is sufficiently unexpected as a function of your degrees of freedom, which is your sample size minus the number of fixed effects, and then your alpha level. So this column right here is for p less than 0.05. That's the traditional level of alpha. That means 95% of the time is expected, 5% of the time is unexpected. So for this column, the present example is based on 100 people, so that's not actually on here. We're down here somewhere around 2. You can put 2 in your head as a placeholder for when t crosses over into unexpected. As you can see, it's a little bit wiggly. The smaller your sample, t needs to bump up a little bit. That's what the t distribution does. It changes shape. It's flatter in smaller samples, but 2-ish is sufficient for most purposes. So if we have a t that's outside of 2, either a positive t that's greater than 2 over here, or a negative t that is smaller than -2. That's when we determine, yes, this is sufficiently unexpected. So if I say it's unexpected, I say my slope is significantly different than 0. I say, what about my null hypothesis? Reject? Reject, yes. So put those together in your head. Unexpected, significant, significantly different than the null. Reject the null. Question?
I got that part, it's the P where I get lost.
The P, yes.
And then what does the, just in lay terms, what does the P tell you? Because I got the reject or you know, or don't reject, but the P is the one that somehow I'm not getting out of.
Okay.
I'm sorry, maybe it's very basic, but.
It's not, that is a common thing that I've talked about with people, so yes, I'm happy to go back over it. So part of your question, I think, lies in differences in how this concept is taught sort of in an old school way using these tables versus what the software does for you. There's a difference in level of precision. So old school, right, I would say my t-value from this example is 4 point something, right? Because 4 point something is out here, it's past my critical point, then I say p is less than 0.05, reject the null, it's significant, the end, right? That is all you would be able to do with this table, is decide, are you in or are you out? Is it p less than 0.05, which is what corresponds to this critical value? Great, you're significant. What the p-value is that shows up in the computer software is much more specific. It's saying, okay, given that your t, say, is 4.9, what is the area under the curve where you would expect that result or something more extreme? So it would be right here is my best guess at where 4.9 is. It's the area under this side that would be a t greater than 4.9 plus the area over here where it would be a t less than negative 4.9. So it's the exact probability of observing a result that extreme if there was no relationship for real in the population, if the null hypothesis were true. So it's not just p less than 0.05. Its p is 0.00002 or whatever. It's a more specific location on this rather than just in or out.
So if the alpha tells us just very basically in or out, right?
Yes, alpha, the way that it's talked about is your a priori decision as to what you're going to call in or out, right? So if I say alpha is 0.05, That means in is 95% of the time and out is 5%. And if I say two-tailed, then it's 2.5% over here and 2.5% on the other side. So in or out, that's it. More specific than that, you can quantify, is it out, meaning it's P equals 0.049, or is it out like P equals 0.00001, right? Those are both out, but that conveys something different.
So one is more out.
One is more out than the other. Yes, you can say that. Out meaning sufficiently unlikely if the null hypothesis were true. And in that case, the null hypothesis is slope is 0.
And so just to recap what you said, when you said when it's unexpected, that will basically be rejected null hypothesis.
Unexpected goes with reject the null goes with is significantly different than 0.
Is there a case when the P was ruled in if you already passed the alpha?
No, they're the same. P is more specific, but alpha is supposed to be the decision point. Let's say that we were concerned about having a false positive. In some situations, a false positive would be worse than a false negative, such as, say, detecting COVID-19, right? False positives would be bad for scaring people. False negatives would be bad in a different way. But if you're concerned about false positives, how do I change what I'm doing here to adjust that, to make it less likely that I'm going to flag something as significant and unexpected just by chance? Do I want alpha to be higher or lower?
Lower, 0.01, right?
Alpha to be lower. So that's what these other options are. For instance, this third column right here. These are what T has to be given these degrees of freedom, which is based on sample size minus the number of fixed effects. If you want to say only less than 1% of the time, you would find something this extreme.
And that's when P comes in.
Then you would not say something is significant unless P was less than 0.01, which is more stringent. So then in, expected, is 99% of the time. Out, unexpected, is 1%. That makes it harder to declare something unexpected. But if I do that, if I use P less than 0.01 instead, then I may have more of the other problem. I may have misses because I've set a higher standard for saying something is significant and unexpected. It makes me more likely to miss something that's really good. That would be making a higher type 2 error rate. So there's a trade-off. You can't have everything at once. If you change alpha to make it more likely to have, less likely to have false positives, then you increase your risk of false negatives, misses. Okay. Does that help?
Yeah, so much.
Good. Good. I'm happy. Other questions on that concept of alpha, in and out? Yeah, so on your homework too, for instance, you were given test statistics of various forms. There are only 4 that will show up in the world. 4 different letters, one of them Greek. Can you name them? Here's one that's in front of you.
Alpha,
One
beta.
statistic that has an associated distribution on which you can locate inness and outness. This one? What's this one called? What's the shape called? What letter? This one's T. No, just regular T. Do you remember the story where T came from? Guinness beer. No, it's a true story. Someone named Gossett was working at the Guinness beer factory, realized that the Z distribution he had been using was flagging too many things as being unexpected, got Guinness to let him go to graduate school to get a degree in statistics, derived the T distribution analytically. It turns out we were actually, this is how big of a quant nerd me and my husband are. We were talking about this yesterday, as one does, you know, in casual conversation. And it turns out that the t distribution actually was derived like using calculus and shit, like in the 1700s. And then someone rediscovered it in the late 1800s, and then Gossett did this, like he found it again using a different method, and that's the one that stuck. And so he wasn't allowed to publish as an employee, so he had to adopt a pseudonym, which was Student's T. Student was his name. And so he published it as Student's T. And so it's the letter T, but it has a convoluted story. So yes, his paper was like 1906 or something. So it's been a while back, but yes, this is T. The other one that's on here, Z, that's the black line. The difference between T and Z as your test statistic, as your location for expected versus unexpected, is whether or not you're paying attention to degrees of freedom. You have to pay attention to degrees of freedom whenever you're trying to run a test on something where you had to estimate the variance first. So in homework 2, you are asked to test a mean of 2 quantitative variables against known values. If memory served, it was fits thrown against 4 and pleases heard against 10, something like that. In that case, it's prop t-test in SAS. What's the stative version? Can't remember. There's a T in front of it. What is the stative version for this? We were just emailing about this recently. It was like, there was a P, it was t-test or p-test. Like, there were two that had, yeah, so I can't remember what it is, but there's a T version where you're testing a sample mean against a population mean where you have to estimate a variance, then that's called, it uses a T. If you're testing a sample proportion against a population proportion, you don't have to estimate variance because in binary data, the variance is determined by the mean, so then you get to use T. But if you have enough people, T becomes Z. So this general shape, whenever we're testing one thing at a time, whether it's a mean against a population mean, whether it's a sample slope against a hypothesized slope of zero, this is how we locate where that estimate is in the expected versus unexpected territory. So these are test statistics. They go with distributions, and the location of your T or your Z on this distribution gives you your p-value. The probability of observing a T or a Z that extreme if the true thing were 0. In this case, it's 0 as the null hypothesis more generally. The other ones, chi-square and F. Those are for testing more than one thing at a time. And so we did Pearson's chi-square for cross tabulations. You'll meet F after spring break. Okay, get out of that. So in this case, we would say our T is significant. So my slope of 6.6 divided by its standard error of 1.35 gives me my T of 4.9. That would be expected less than 5% of the time. And so it is significant. What that also means at the same time, homework question. If the slope is significant, if the slope is sufficiently unexpected, if the true slope were 0, that has to mean that this difference in residual variance is also unexpected, is significant. They go together. The slope is the only thing that we added. So if that slope by itself is significant, that means the difference in residual variance it caused, the amount of variance that it explained by changing this regression line to be this slope instead of a flat line, that change in variance has to be significant too. there's a one-to-one mapping in this case because there's only one predictor. And I'm hearing a phone or a lullaby, one of the two. Sounds like a lullaby phone. All right. Questions from either the in-class people or the Zoomers? No, we're good? Do you want to see it in software again? Make sure you know what to do on your homework? That'd be good? Okay. So, question that Jacob had, he was talking earlier in class, he was wondering, am I supposed to be memorizing all of these SAS commands? No, decidedly not. My strategy here is to give you templates that you can use in the future to do things with, because I don't have this stuff memorized either. Things I use every day have crept into my memory, but I still usually copy from something else just to make sure that it's exactly right. So I'm offering you more things in here than I'm asking you to do in homework, because this is supposed to be for future reference. So part of the difficulty I found in answering questions is figuring out which of these things is necessary for you to have to do to be able to answer the questions. So in homework 3, it's going to use the same data from homework 2. You're going to be predicting each of the quantitative outcomes from the other quantitative predictor and a binary predictor. So in order to do that, this is example 3, you will need to do at least the part that's on the first page here. So in SAS, you'll have to tell it where your data file is and run the code to import it into SAS. Here's what that would look like in Stata, to tell it where your data file is and run the code to import it. The only catch is that in this example, I'm importing a Stata dataset. In your homework, you're importing Excel. So every time I give you a homework, I give you a starter syntax that has code to import Excel. Use that to do that part. The other thing that you'll have to do is center your quantitative predictor. So centering is the process of subtracting a constant from the variable. So here's an example of how to do that, just this little part right here. In SAS, it's new variable equals old variable and what you want to do to it. So education 12 is a new column I'm creating in my data set from a current existing column called education, and then subtracting 12 from every value. For transparency, I'm also attaching a label to it so that if I ever were to go back to this and say, what the hell is EDEC 12? I would know what that means. The analogous command in Stata is right here. The only difference is the word gen in front of the new variable you're creating and the absence of a semicolon at the end of the line. Labeling variables in Stata looks the same. It's the command label variable, the variable name, no equal sign, and then a label. Things like labels are good practice. They're not strictly necessary when doing your homework. Okay. Questions on any of that so far? Okay. Then here, descriptive statistics. I'm providing these for reference for this example. This isn't something that I'm asking you to do for homework 3 because you did it in homework 1 and 2, so I thought that's enough practice with that. But in general, prop means and Stata summarize. Those are how you get descriptive statistics for quantitative variables. So that includes measures of central tendency, dispersion, minimum, maximum, and that kind of stuff. So in terms of what it would be helpful for you to memorize or recall, just know that if I have a quantitative variable and I'm using SAS and I want to know what its mean is, that's prop means. That will be enough for you to search through this handout or the syntax files or the internet to find the rest of how this should look. Likewise in Stata, if you're trying to get descriptive statistics for a quantitative variable, the command is summarize. So here are the descriptives for family income in its various forms, education. We're also going to look at a binary predictor later on. Here's an example of something I'm providing for your future reference, but you don't ever need to do in homework. Histograms. Making pictures to describe what your data look like is always helpful. That's not something I'm going to grade you on, but it's something I wanted you to have a copy of in terms of how to do it, so I put that in there. To get correlations between quantitative variables or binary variables, that is proc core in SAS or PW core in Stata. So we're looking at correlations between the variables of interest. I want to point out this one in particular because we're going to see the same value show up in the modeling. The Pearson correlation between years of education centered at 12 and family income in thousands is 0.45. So that is an effect size. A Pearson correlation, like any kind of correlation, ranges from -1 to 0 to 1, where 0 means there's no relationship. The fact that this is a positive number tells me what?
It's got a positive correlation.
Yeah, as education goes up, income goes up. Or if you want to say it the sadder way, as education goes down, income goes down. Both of those are accurate. Up is usually the way people talk about it. So is this different than 0?
Yes.
It looks like it should be, but here's the thing that tells me for sure. This little piece right here, what is that? SAS tries to help you with a label that SAS thinks is perfectly clear, and if it were, I wouldn't have a job. This is the probability of seeing an R
Correlation.
absolute value, right, greater than, so more extreme than 0.45 positive, or more extreme negative than negative 0.45, under HO, rho equals 0. So putting that together, it's the probability of getting a correlation more extreme than 0.45 if the null hypothesis were a correlation of 0. So if there were no association at all, correlation of 0, by what probability would we see something this extreme?
Very, very rarely.
So this less than sign is SAS's way, hey, stop that, of just giving up and saying it's 0 to at least 4 decimal places, less than 0.00001. So in terms of our decision, what does that tell us? The fact that it is less than 0.05 means what? Not significant or is significant?
Significant.
Less than 0.05 means that we have headed into unexpected territory. If our alpha is 0.05, that's our cutoff. So the fact that this p-value is less than 0.05 means significant. So putting that more specifically, what is significant? R is. This correlation of 0.45 is significantly different than 0. We would expect to see a correlation that big if the true correlation were supposed to be 0, less than 0.01% of the time.
Yep.
Very unexpected. You might be tempted to say very significant. Don't say that. Exactly. It's either significant or it's not. The fact that it's very significant, if I can borrow that phrase for a moment, tells us more about sample size. Because in order to know whether or not this R is significant, SAS is skipping a step that it's doing behind the scenes that it's not showing you. It is computing a t-test statistic for this R and then giving you the probability of observing a t-test statistic that big. And the other thing that you have to know to calculate t besides the R itself that it's testing is sample size. So whether or not a correlation of 0.45 is significant depends on your sample size. 0.45 is the effect size. Doesn't care if you're testing this on 10 people, 100 people, or 1,000 people. Whether or not that 0.45 is different than 0 depends on how precise of an estimate it is. And that depends on its standard error, which is a function of sample size. But this 0.45 is my effect size for the bivariate relationship between education and income, meaning just the pair of them together. That number is going to show up in my output from my linear model as a standardized slope estimate. So here's where all the numbers in these slides came from, such as the numbers for this picture with the empty model, and then adding education as a predictor. Here's my empty model. By the way, for the rest of the semester, this is all you need to know. Proc, GLM, and SAS, that's how we're going to run linear models. Regress and stata. Regress. Yep. That is short for regression. GLM stands for General Linear Model, which is the umbrella term that describes any time you're predicting a continuous outcome whose residuals are supposed to follow a normal distribution. We'll get into more of that nitty-gritty next. I just wanted to give you a feel for how to talk about slopes and such. So if you were to borrow this code, stick it in your homework folder, or your syntax file, and run it, what will happen? Say louder. Only if you have my data. Yeah, well, so I've watched this happen. People borrow this, copy it into your syntax and run it. And SAS is angry with you because it says, hey, I don't have a work.example3 data set. I have no idea what you're talking about. And I don't know what this is either. Because these are tied to the data. The data set that's being used for this analysis is called work.example3. So you'd have to change that to what your homework data set is called. Likewise, this FAM Inc. 1000 is a column specifically in this example data set. You don't have a variable called that, and so it will yell at you if you try to ask for it. So here is where your outcome variable would go instead. And likewise in Stata, it's just this much. Stata has a lot less code associated with it. The other stuff that you can change in SAS, I've listed here. You will rarely have to change it, if ever. After a slash is how you denote options. The word solution here means, hey, can I have my actual slope and intercept estimates, please? Because that's not a default. By default, it does not show you the answers. Bad human factors. Alpha equals 0.05 and CL par. What do you think that does? Feel free to read from the screen. Yeah, confidence limits. So sometimes you'll see CI, sometimes you'll see CL. It's the same idea. It's the boundaries of where expected and unexpected are relative to that particular estimate. If you want to change these boundaries, so if I say alpha equals 0.05, then the confidence limit I'm asking for is 95%. If I asked you in your homework to do, say, alpha equals 0.10, how would I fix that? Watch carefully. And then the confidence limit I get back is not 95%. What is it instead? 90. So we're moving in the boundaries of where unexpected starts.
Push, 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 push.
I'm not going to have you change it from 0.05. I just wanted you to be able to. In SAS, all procs end in a run to make it go. Some of them also need a quit. It seems redundant, but it's actually not. Question from the Zoomers. Let me see. So we can hear you typing. Okay. Can you not see the screen? Oh, they're talking amongst themselves. Okay. Yes. Carry on. The muting. Yes. So the results of this output here in SAS, the Stata results look very much the same. I told you you can ignore all of this stuff for right now except for this one number. That's your residual variance. That is the variance of the e's given the model that you just fit. If you have no predictors in your model, if this is an empty model, which is what we're talking about right now, here's my empty model, then this is all the variance in your outcome. If I have no predictors, my fixed intercept estimate right here, that's what its best guess for what beta 0 should be. 40-ish. So on your homework, I'm going to ask you to fill in each of these values. Enter the estimate for the intercept. That's this column. Enter the standard error for either an intercept or a slope. That's right here. Enter the t-value that goes with it. That's right here. So the 39 divided by the 4 is this 8.74. It does the math for you. This thing here, that's your probability. That's your p-value. It's the probability of observing a t that extreme. So this t is testing this mean of 40 against a null hypothesis of 0. So 40 is very unlikely if 0 were true. So it's saying that's going to happen less than 0.01% of the time. If we add in original education, so note that this is not the centered version, this is the original version. I'm doing this for pedagogical reasons. That new predictor variable goes right here in SAS. So model y equals x is the way to read this. It works very similar to the equation. The beta 0 is implied. You don't have to type it. It always gives it to you. But you do have to ask for a slope for any other predictor variable that you want. Likewise in stata, y immediately followed by x. Order matters. Always y first, then x. And there is no way that you would know that just from looking at the code. I know, this is why I have a job, people. They don't make it easy. On the one hand, there's much less typing. On the other hand, you have to know exactly what you're doing. What would happen if I forgot and I switched these two? What would it do? It would shift the chart. It would predict education as an outcome from income as a predictor. Did you have a question, John Paul?
No, just, I noticed just popped up, I know, just did some class.
Oh, Cornell's down too. Great.
Or Grinnell, I'm sorry.
Grinnell or Cornell?
Grinnell.
Grinnell. Okay, well, I'm not sure that changes my opinion. I'm going to go with the sarcastic. Great, either way. This is, I'm wondering if I should go read up on The Stand by Stephen King again, just to get my, get in the superflu sort of mood here. The what? Blindness? Jose Saramago? Saramago. Okay, there's another one. End of the World Lit is going to be quite popular, I think. Post-apocalyptic, yes. Yeah, The Stand is the classic. That's probably my favorite book, as dark as it is, but it is. It's dark.
Just make sure that everybody's still accurate. So y, which is the first one, that's the output.
Yes.
Right. And then the second one is always accurate.
Yes. 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 So the first word here is the column that you want to be the outcome. The next word or words are the predictors. So if I had more than one, I'd just keep typing and list them all. But there's nothing that tells you which is which unless you just have that memorized. Whereas in SAS, there's an equal sign.
No.
Is the amount of error variance residual variance number. That's the 1594.
No.
And here's my solution.
No.
So without centering education, I get answers back that are not wrong, but they're weird. What's weird about this? That's weird. Yes, your income is minus $52,000 as the model reference point. We're still talking about muting amongst ourselves. Okay. So that's not wrong in the sense that the regression line keeps going and going and going, but it's weird because for what kind of reference person am I predicting an income of negative $52,000?
Come up here. All the way.
Somebody who went to 6th grade?
Somebody who's 0 years old. Yeah.
0 education years, not even 6th grade.
Oh, it's not.
It's education in its original metric where 0 means no years. And here's a scatter plot that shows the prediction from this model. There's nobody out there. The lowest in this data set is 5 years of reported education. But the line keeps going. So if you extrapolate along this regression line,
Extrapolate
you
along
get
this
the minus
regression.
$52,000 over here at 0. So there's nothing wrong with the model, but having an intercept that's impossible is not so helpful. So we're going to skip that version in your homework, and instead, when you enter a slope of a quantitative predictor, I want you to do so using the centered version. So you'll have to make a centered version first, and then use that as the predictor. So I'm adding in education 12 instead of original education in both of the places.
Got it.
The rest of this code for Stata, this is making pictures. So you don't need this in your homework unless you'd like to make some pictures too. There is one thing that I've added to Stata that is not yet relevant in SAS, and that's this thing beta. That is going to add a column that gives you standardized slopes and intercepts. Meaning after correcting the scales of the variables to each have mean 0 variance 1, there's an analogous command to do that in SAS, which is proc reg instead of GLM, with the option STB, standardized beta. That shows up right out here. So putting it all together, in the original unstandardized solution, that's phrased in terms of dollars and years of education. My new model says that somebody with a high school degree, education equals 12 as my new reference point, is predicted to make $27,000 a year. For every additional year of education past 12, my income is predicted to go up by $6,600. If I translate those two fixed effects, the intercept of 27 and the slope of 6.6, into standardized versions, meaning I go from dollars and years to z-scores, mean 0 variance 1, that gives me these out here, the standardized estimates. The standardized version of your intercept will always be 0. Always, 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 always. The standardized version of your slope, if you only have one quantitative predictor in the model and you ask for a linear slope of it, that standardized slope is your Pearson correlation. That's the 0.45 we saw earlier. The p-value that goes with it is the same p-value of 0.0001, and here's the t-value that it hid from you in Proc Core that's now showing up. So like 20 minutes later, I've just shown you the Pearson correlation again. But why am I bothering? I can think of 3 reasons why doing it this way, rather than just running the correlation, is potentially more useful. We talked about this last week, maybe. What kind of association between quantitative variables does a Pearson correlation reflect?
Type of relationship.
Starts with an L.
Linear.
Yeah, the linear. Linear, right? Let's look at my model. It's a linear effect of education. Beta 1, the slope, says for every additional year of education, income goes up by beta 1. Same, they're lockstep. But in reality, do you think that there's a nonlinear relationship that's possible? Does more education help, but only up to a point? Yeah, this model and that Pearson correlation aren't going to capture that. Okay, now my screen is like angry with me. Okay, there we go. So one of the reasons why you might fit a model instead is to be able to look at nonlinear effects of quantitative predictors. The idea that maybe it's best to have a middling amount and that either too much or too little is not so good. Or effects of slopes that sort of degrade as you get higher on, asymptotes, so to speak. The other one, credentialing.
Let's look at it.
Yeah, I mean, we're talking about as if one more year means the same thing. It doesn't, right? In reality, there's 12, and then there's bachelors and there's masters, right? And like one more year doesn't count unless it results in another degree. None of that is represented in this oversimplification. But wait for it, it's coming next time. Not next week. Next week is spring break, but after that, yes, we're going to look at, we're going to change the model to include piecewise effects of education, meaning a different slope if you're talking about pre-high school than if you're talking about bachelor's level than if you're talking about graduate level. Because 1 year is not equal, right? Yes, thank you for that foreshadowing. The other thing, what if you have non-quantitative predictors? What if I wanted to know if family income was related to favorite TV show? It's categorical, yeah. Can I take favorite TV show and put it in the model like this? Where 1 is, since we're talking about adults here, 1 is Grey's Anatomy. 2 is Law and Order Special Victims Unit. 3 is The Prophet on CNBC. Those happen to be my favorite shows. Oh wait, 4 is This Is Us. I got to put that one in there. You're going to hear more about that later this semester. I've got a whole thing with that. But yeah, so I want to see if people who make more money, if people who like This Is Us make more money than people who like Grey's Anatomy. Can I draw a line through favorite TV shows 1, 2, 3, 4? SAS will let you, but it doesn't mean anything. Yeah. If I have 4 favorite TV shows, I'm going to have to draw 3 lines because I'm going to have to differentiate a reference TV show from each of the others. So that's another reason to do a model instead. And then last but not least, what about multivariable associations? What if I want to know if education is still related to income after controlling for gender, race, location of rural versus urban, that kind of stuff, right? Can I do that in a Pearson correlation? There are correlations that are designed for that, but they only work with quantitative variables as the extras, and so modeling is, again, way more flexible. So yeah, in order to say, does beta 1 still matter after putting in other stuff? I got to put the other stuff in the model. And then what happens to these slopes is that they become what's called unique effects. What is the effect of education after controlling for race, gender, location, etc., etc.? And each of those is conditioned on the others too. So that's how we try to pull apart things in the real world that we can't use experimental control for. We can use statistical control to see what the net effect of something is after factoring in other stuff it's related to. So those are 3 reasons why this is not a waste of time. If you understand linear models, if you understand how to translate hypotheses into these kinds of terms, it's very, very powerful. That's what I want to give you after spring break. And here's some pictures. So wrapping up in terms of the code here, since we're out of time, to get unstandardized coefficients, intercepts and slopes, that's proc GLM, or regress in Stata. To get the standardized versions in Stata, all you have to do is add that option beta, and you get that too. In SAS, you have to switch to proc reg instead of proc GLM. Reg is an older procedure. It doesn't have nearly as many options available within it as GLM, which is why I'm preferring GLM. But they do the same thing in this very limited case with the additional option to get you this column out here. So there should be no hand calculations whatsoever. Okay? If you want to, if it makes you feel better to calculate things, you got all the formulae. You can do it if you want. That's fine, but you don't need to. In just the standardized versus unstandardized, just to remind you that that is in here too. That's on slide 10. Here's the conversion of how you go from an unstandardized effect to a standardized effect. You need the standard deviations of each of the variables involved to be able to do that. Okay. All right, any questions? Okay, then you can do 2/3 of your homework right now. After Thursday, we will do the binary predictor that remains, just a few more slides, and then you'll be able to do all of it. Okay? It is due the Friday after spring break. So a full week and a half of regular classes, even if you take spring break off and do not this. I just expect that you do, right? Either you're catching up on other things or you're catching up on life, which I highly encourage everyone to do, by the way. Don't run yourselves ragged. Self-care, lots of Grey's Anatomy, or knitting, or maybe even exercise, God forbid. You know, it's been a long time since that's how I self-care. All right, any questions before we adjourn? Alrighty then, I will see you Thursday. Stay well. Let me know if you need anything.